2.0.0 Scale Drawings. Explain how to measure items on a scale drawing. Describe how to use an architect's scale. Describe how to use an engineer's scale. Describe how to use a metric scale. Then there's a performance task using an architect's scale. State the actual dimensions of a given drawing component. Your instructor will probably have you do that. It says the components in most electrical drawings are too large to draw in actual size. To fit them on a sheet, drawings are scaled down to reduce the size. When you read electrical drawings, you must know how to interpret the scale so you can determine the actual size of all the components. If you ever have to create an electrical drawing, you must know how to reduce the components to scale. In this section, you learn how to use a scale. 2.1.0 Drawing to Scale. All right, I'm not going to read all of this. What they're saying is that to scale something up is to make it larger than normal, and that's to show detail. If you were drawing something small, like if you wanted to draw a bolt, let's say, you could draw that bolt at 2 inch equals an inch and draw the bolt twice the size that it actually is in real life. If you were to draw to a 1 inch equals 1 inch scale, it would be drawn to actual size. Most of all of our drawings are scaled down. So here, a half an inch equals an inch. So when you draw this, you'd end up with a drawing of the bolt that's half the size of the original bolt. 2.1.1 Understanding Scale. To understand a scale drawing, you must understand the relationship between the actual dimensions of an object and the dimensions of a distance shown on the drawing. For example, to draw a floor plan of a 40-foot by 20-foot building using a scale of 1/4 inch equals 1 foot, each 1/4 inch on the drawing equals 1 foot on the building itself. So if we multiplied 40 feet times 0.25 inches, we'd end up with 10 inches representing that 40 feet. And 20 feet times 0.25 inches equals 5 inches. So we would be drawing 5 inches by 10 inches, and it would represent a 20 by 40 building. Drawing of the building would be 10 inches by 5 inches. If the scale is 1/8 of an inch equals a foot, each 1/8 inch on the drawing equals a foot of the building. So we would multiply times 0.125, which is 1/8. And we'd get 40 times 0.125 is 5, and 20 times 1.125 is 2.5. We'd end up with a drawing that was 5 inches by 2.5 inches. Scale used for architectural and engineering drawings is very important. Drawings must be easy to read and understand. When buildings and systems must be built to very accurate standards, the scale dimensions should be as large as possible. The drawing should also include dimension lines. When dimensions require only reasonable accuracy, the object may be drawn to a smaller scale and the dimension lines may be left out. So take a look at the floor plan, figure 15. You'll see that one wall is drawn on the sheet as having a distance of 3.5 inches. Of course, the actual building does not have a 3.5 inch long wall. If the distance between the arrowhead measures 3.5 on the construction drawing, the drawing is made to a scale of 1/2 inch equals 1 foot, and the distance between the arrowheads represents an actual measurement of 7 feet. So in real life, this is 3.5 inches on the drawing, but it's representing a wall that's 7 feet long. Caution, when drawings are printed or plotted, they're often printed to a size that fits the paper rather than the size equal to the scale used when the drawing was made. You should always double check the scale against a marked dimension on the drawing to get the correct drawing scale. This will help you avoid errors in layout and material ordering. This happened to a job I was on. The plot printer, when they printed the blueprints that they had drawn very accurately, the dot matrix printer put a 1 inch border around the entire blueprint for some reason. So it took the blueprint and just foreshortened it ever so slightly. But that meant that all of the measurements were off. It was not scalable. You couldn't take a 1/4 inch equals a foot or an eighth of an inch equals a foot scale and scale it accurately. You had to use a multiplier of like 0.9875 or something. We had to figure out what the multiplier was, and then we had to use it to convert all of the measurements that we needed. 2.2.0, using an architect's scale. When you make a measurement on an actual building, you use a standard foot rule. When you make a measurement to scale, you use a scaled ruler. A scaled ruler is a tool for measuring lengths and transferring the measurements proportionately. The most common scaled rulers used in electrical drawings are the architect's scale, which measures in inches or fractions of an inch, and the engineer's scale, which measures in decimals. For drawings that use metric measurements, a metric scale is used. So this architect's scale is a special ruler that allows you to measure distances on drawings as real-world distances in feet, inches, and fractions. An architect's scale measures distances in inches, and it's usually a 1/4 of an inch equals a foot or an eighth of an inch equals a foot. An engineer's scale is a special ruler that allows you to measure distances on drawings as real-world distances in decimals. An engineer's scale measures distances in decimal units. Usually the engineer's scale is a lot larger of a scale. It might be 1 inch equals 50 feet. This allows you to draw a much larger area on a piece of paper. 2.2.1, using a flat architect's scale. One common type of architect's scale looks similar to a standard ruler. As the name implies, it is flat and has one or more series of measurements or scales. Figure 16 shows a flat scale with a 1 inch equals 1 foot scale. Refer to the 1 inch scale, which shows subdivisions of 1 foot. The longer marks to the right of the 0 represent feet. Therefore, the distance between 0 and the longest mark, 1, equals 1 foot. To the left of the 0, the shortest lines represent half inches, and the longer lines represent inches. Note that 3, 6, and 9 divisions are numbered. So here's the 0, and here's 1 foot when you're talking about 1 inch equals 1 foot. This is 1, 2, 3, 4 feet. Going to the left of the 0, these are inches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are all inch marks. That way you can use it to measure feet and inches. 2.2.2, using a triangular architect's scale. Another common type of architect's scale is a triangular scale. For example, figure 17 shows a triangular scale with 3 sides or faces, each having 2 edges. This means there are a total of 6 edges on the triangular scale. Each edge has 2 scales that start on opposite ends. So if you look at this carefully, you'll see that 1/8 of an inch equals a foot starts on the right and moves over to the left. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You have to keep your wits about you when you're reading these. So 1/8 of an inch scale is 4, 8, 12, 16, 20, 24, 28, 32. When you're talking about the 1/4 inch scale, they start from the left side here and they go to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can notice that the 1/4 inch scale goes up by 2 feet. The 1/8 of an inch scale goes up by 4 feet. So 0, 2, 4, 6, 8, 10. This is 0, 4, 8, 12, 16, 20. The scales on each edge are as follows. Common foot rule, and 1/16 of an inch equals a foot. And 3/32 equals 1 foot, and 3/16 of an inch equals 1 foot. 1/8 of an inch equals a foot, and 1/4 of an inch equals a foot. 3/8 of an inch equals a foot, and 3/4 of an inch equals a foot. 1/2 inch and 1 inch, and 1 1/2 inches, and 3 inch. 2 separate scales on each face may seem confusing at first, but after gaining experience reading these scales, it'll become second nature. On the 1-inch face, the 1-inch scale is read from left to right, starting from its 0 mark. The half-inch scale is read from right to left, again, starting from its 0 mark. So here is a 1/8 equals 1 foot scale. And we wanted to measure the distance of this wall. So we first measured full feet going 4, 8, 12, 16, 20, 24, 25 feet. But then it was longer than 25 feet, so we moved the ruler off of the 0. We moved the 25 over to the edge of this wall. Now we can read 25 feet, 6 inches. This represents a foot, so half of it represents 6 inches. Each one of these demarcations is 2 inches, 2, 4, 6, 8, 10, 12. So this is 25 feet, 6 inches. Caution, it's not uncommon to have several different drawings or details on one blueprint sheet, all with different scales. Always check the scale of each view found on the drawing set. To find a dimension, place the 1/8 inch architect scale on the drawing and read the figures. The two sets of numbers along the scale can be confusing at first. Just remember to use the numbers that count up from 0 at the end with the same scale marking as the one in the drawing. In figure 18, you're using the numbers closest to the edge of the scale, which line with each line representing 1 foot. Not that the numbers farther from the edge with the longer lines representing 1 foot. The dimension in the question is 25 foot. They're saying 25 feet 3 inches. See, I'm going to argue with them. They said 25 feet 3 inches. I'm going to say it's 25 feet 6 inches because this is a whole foot. This is a half a foot. That's 6 inches. All right. I guess I should write the editors. 2.3.0, using an engineer's scale. Site plans are drawn and read using the civil engineer's scale rather than the architect's scale. The main difference between the two scales is that the engineer's scale uses decimal units of 10, 20, 30, 40, 50, and 60. You can look at the decimal value on the engineer's scale and convert to measurement in feet. Another difference between the scales is that the engineer's scale has 2 measurements per face, but only 1 on each edge. Okay. So here's the engineer's scale. Let's see here. On a small lot, if you're using an architect's scale, you usually use a scale of 1 to 10. 1 inch equals 10 feet, or 1 to 20. If you're using an engineer's scale, the scale would be 1 to 10. 1 inch equals 10 feet. That means that 1 inch, the measurement on the drawing, is equal to 10 feet on the land itself, or 2.4 inches equals 24 feet on the land. On larger drawings where the large area must be converted or covered, the scale could be 1 to 100. 1 inch equals 100 feet, or 1 to 1,000. 1 inch equals 1,000 feet, or any other integral power of 10. On drawings with a scale in multiples of 10, if you use the engineer's scale marked 10, if the scale is 1 inch equals 200 feet, use the engineer's scale marked 20, and so on. Using a metric scale, 2.4.0. Metric scales, like engineer's scales, use units of 10. However, metric scales are calibrated in metric dimensions instead of inches and feet. The two common length measurements used on metric scales on architectural drawings are the meter and the millimeter. That is a highlight. Two common length measurements used in metric scale on architect drawings are meter and millimeter. The millimeter is 1/1000th of a meter and is typically used on drawings with the scales between 1 to 1 and 1 to 100. The meter is generally used on drawings with scales between 1 to 200 and 1 to 2000. Many contracting firms working in international trade use a dual dimension system with measurements in both metric and imperial units of distance. Drawings prepared for government projects may also require metric dimensions. For a detailed metric conversion chart, see Appendix 26110.23a. Here's Section 2 review. And as always, I'll let you answer these questions. If a floor plan of a building is drawn to a scale of 1/8 of an inch equals a foot, a distance of 1 inch and 3/8 on the drawing would equal how many feet? The most common scaled rulers used in electrical drawings are the what? Using a 1 to 20 scale on an engineer's scale, a measurement of 2 inches on a drawing would equal how many feet? And a metric drawing scale of 1 to 1,000 typically depicts units in what? All right, very good. I'll see you on the next video. Thank you. 3.0.0 Electrical Drawings. Identify information on electrical drawings. Identify electrical symbols. Identify information on residential electrical drawings. Explain how to read a set of commercial plans. Describe how to read schedules, block diagrams, and schematic diagrams. There is a performance task. Your instructor's going to want you to make a takeoff list of luminaires from a drawing. So you'll have to tell them how many and of what kind of luminaire lighting fixture to order. An electrical drawing shows exactly what is required of you as the electrician in a clear, concise manner. They're usually prepared by the engineering firm consulting on the project. As an electrician, you must be able to work with electrical drawings prepared by different people using different drawing techniques. In this section, you'll learn to read and interpret electrical drawings. 3.1.0 Reading electrical drawings. The amount of data shown on electrical drawings should be sufficient but not overdone. This means that a complete set of drawings could consist of only one 8.5 by 11 sheet, or it could consist of several dozen 24-inch by 36-inch sheets, depending on the size and complexity of a given project. A set of working drawings for an industrial installation may contain dozens of drawing sheets detailing the electrical system for lighting and power, along with equipment, motor controls, and wiring diagrams. A schematic diagram and equipment schedule may contain other pertinent data. A schematic diagram is a type of drawing in which symbols are used to represent the components in a system, also referred to simply as a schematic. So in general, there are 3 reasons for the use of electrical working drawings. They provide an accurate description of the project, so the electrical contractor can estimate materials and labor to calculate the project's total cost for bidding purposes. They provide workers with information about how and where the electrical system is to be installed. They provide a map of the electrical system once the job is completed to aid in maintenance and troubleshooting for years to come. Here's a highlight. It says, sometimes electrical contractors will have electrical drafters prepare a shop drawing or vendor drawing. This is a special supplemental drawing for use by the contractor's employees. Shop drawing is a drawing that's usually developed by the manufacturers, fabricators, or contractors to show specific dimensions and other pertinent information concerning a particular piece of equipment and its installation methods. 3.1.1 Electrical symbols and lines. As an electrician, you must be able to correctly read and understand electrical working drawings. This skill requires a thorough knowledge of electrical symbols. So they use symbols on a drawing rather than trying to pictorially draw each item. They don't draw a receptacle, they draw a circle with 2 lines through it, and that represents a duplex receptacle. It says here the electrical symbols described in this section are found on actual electrical working drawings throughout US and Canada. Many of them are symbols recommended by the American National Standards Institute, ANSI, and the Consulting Engineers Council, CEC. Understanding how these symbols are used will help you interpret unknown electrical symbols in the future. So we're going to use the letter S for a switch. This is a single pole switch. Here's a double pole switch. or a three-way switch, or a four-way switch denoted by the subscript. There's a key-operated switch or a pilot switch, so a switch with a pilot light. There's a low voltage switch, a switch and a receptacle, a switch and a duplex receptacle. This circle with two lines, that was the duplex receptacle we were talking about earlier. Here are receptacle outlets: single receptacle, duplex receptacle, triplex receptacle, split wired receptacle, they'll shade one side of it. Single special purpose receptacle is a triangle and a circle. Duplex special purpose receptacle, they've got two lines coming off of it. A range receptacle has three lines coming off of it. It's 250 volt, that's 50 amp. Special purpose connection or provision for connection. Subscript letters indicate the function. W is dishwasher, CD is clothes dryer, etc. There's a clock receptacle with hanger, a fan receptacle with hanger, a floor receptacle. So all of these are things that you might see on the drawings. Here's a wall-mounted fixture or a ceiling-mounted fixture. There's a surface fixture with a pull chain, PC, a recessed fixture with an R, a surface or pendant fluorescent fixture. There's a recessed fluorescent fixture. The R is for recessed. Here's surface or pendant continuous row of fluorescent fixtures. Usually we're just going to feed one of those fixtures in a line, and then we'll daisy chain the others. They'll all come on the same circuit. Here's the same thing, but the recessed. Surface exit light, wall-mounted exit light, recessed exit light, blanked outlet or a junction box. Here's the different circuit wires. A more comprehensive list of receptacle symbols is shown in Figure 22. Note that each starts with a circle, but an addition of one or more lines crossing the circle and a few abbreviations gives individual meaning. So again, we went over these. It's a single receptacle, duplex receptacle, triplex receptacle. This is a quadruplex. Here's a 250 volt single phase receptacle outlet, 250 volt three phase receptacle outlet. Here's a duplex split wired receptacle, triplex split wired receptacle, single special purpose receptacle. There's a GFCI. There's a range outlet, dishwasher, clock outlet, fan receptacle. There's a floor single receptacle or a duplex receptacle. There's a floor special purpose outlet. There's a telephone outlet. Here's a private telephone outlet. Single receptacle outlet with a USB port and a duplex outlet with USB ports. A light fixture, luminaire symbol, also starts with a circle representing a ceiling-mounted luminaire. The addition of a short line indicates wall mounting, and a rectangle or long line indicates fluorescent or other strip-type luminaires. These type of luminaires, the type of luminaire is usually defined by the numeral placed inside a triangle or other shape placed near the luminaire. They'll call it out on the fixture schedule. You can have drawings on the reflected ceiling print, and then each one of these luminaires will have some kind of a number by it, and it'll tell you in more detail in the lighting outlet schedule what those are. A complete description of the luminaire identified by the symbol should be found in the luminaire schedule. You know what? That is a highlight. On the drawings or in the written specifications and fixture submittals. This description should include the manufacturer, the catalog number, the number and type of lamps, the voltage, the finish, the mounting, and any other information needed for the electrician to properly install the luminaire. Switches used to control luminaires or switched receptacles usually begin with the letter S, followed by a number or letter to define the exact type of switch. For example, S subscript 3 indicates a three-way switch. S subscript 4 identifies a four-way switch. S subscript P indicates a single pole switch with a pilot light. A curving line or a subscript letter can be used to match a switch to the luminaire it controls. Rectangular box is used for a main distribution centers, panel boards, transformers, safety switches, and other large electrical components. A detailed description of the service equipment is usually given in a panel board schedule or the written specifications. However, on small projects, the service equipment is sometimes indicated only by a symbol and notes on the drawings. Other symbols are simplified pictographs or a box combined with a pair of lines representing an external handle. Yeah, we've got a rainstorm going. I hope that's not messing up the video that much. I might have to reshoot it later. Here are the pictographs. There's a double floodlight. Here's a fusible safety switch. This is non-fused safety switch. A double throw safety switch. Lines on drawings used to represent circuits and their related components. Most circuits concealed in the ceilings or walls are indicated by a solid line. A broken line is used for circuits concealed in the floor or ceiling below. An exposed raceway are indicated by short dashes or by the letter E placed at intervals along the same plane with the circuit line. The number of conductors in a conduit or raceway system may be indicated by short dashes on the drawings or in the panel board schedule. All right. The electrical symbols shown in Figure 24 are examples of symbols selected by an engineering firm for use on a small industrial electrical installation. In addition to the receptacle symbols shown in Figure 22, the other groups of electrical symbols recommended by the CEC are shown in Figure 25A and 25B. Additional groups of these symbols are shown in Figures 25C, D, E, F, and G. As you progress in your learning and experiences, you'll readily encounter and use these types of electrical symbols. So here are some symbols used by the electrical firm. Underfloor duct system with a junction box and 3 ducts. Here's dotted lines indicating blank ducts. GE type LW223 lighting busway. Here's type 326 lighting busway. Type DK100 busway. Busway feed-in box. Here's a panel, lighting or power panel. Conduit concealed above ceilings or walls. Here's a motor connection. Here's a toggle switch with thermal overload protection. Duplex receptacle, grounded. And again, we have the switches, key operated, fuse stat holder, pilot lamp, fan switch, low voltage switch, a master switch for low voltage switching system. All of these different schematics, all of these symbols, you're going to be exposed to them. You'll get used to them. There's a handoff automatic control switch, multi-speed control switch. Usually in the handoff automatic, in one position it's on. Whatever it is that you're controlling is just running. You turn it on, it's on. Off, it's off. When you put it to automatic, it gives the control to something else, like a float switch or a pressure switch or a temperature switch. Something will determine when this thing will come on, whatever it is that you're controlling. So you can turn it on and off, or you can let something else determine when it comes on and off. Multi-speed control switch or a push button. And then there's a whole slew of different here electrical cabinets, panels. There's a termination cabinet. This is flush mounted. This is or surface mounted and flush mounted. Your motor or other power controller, maybe starter or a contactor. Here's a disconnect switch. Combination controller and disconnect means. There's a transformer, push button, float switch, limit switch, pneumatic switch. All of these different things you'll see used on some drawings. Not on every drawing, but on some drawings. Ceiling or wall mounted exit lights, blanked outlets, junction boxes. Here's a fluorescent light. There's a whole string of fluorescent lights together. So go through these. If there are any symbols you don't understand, ask your instructor about them. Samples of individual items indicated, identification not a part of a standard. So these are different notes that go with the items on the drawing. Okay. Sound systems. Public telephone system devices, private telephone system devices. All right, very good. These are more residential. Push button, a buzzer, a bell, combination bell buzzer, a chime, annunciator. There's an electric door opener, interconnection box, bell ringing transformer. There's an outside telephone, interconnected telephone. Okay. 3.2.0 residential electrical drawings. Most residential projects have a very basic set of drawings created by an architect or an electrician on the job. Homes with complex installations such as smart appliances, alarm systems, and technical lighting may have complete electrical working drawings and specifications similar to those for commercial and industrial projects. A set of residential electrical drawings may have 1 to 3 sheets. They're easier to read and use than commercial or industrial drawings. However, the drawing details such as lines, symbols, and branch circuiting are the same for residential projects as for commercial and industrial projects. A lot of times the wire circuiting will be done by the electrician. It won't be on the drawing. They won't tell you how to take your home runs to the panel. They'll allow you to circuit the house in the most efficient way. 3.2.1 branch circuits. Here's a highlight. It says the maximum load on the circuit is the reciprocal of 125% is 80%. So basically the required number of branch circuits for lighting and receptacles depends on the building's use or occupancy. Article 220, Part 2, Sections 220.10 through 220.16 provides information on calculating branch circuit loads for various occupancies. Since these branch circuits are considered continuous loads, 210.19A1 states the minimum conductor size must have an ampacity of not less than 125% of the continuous load. So the circuit breaker has to be 125% of the load. The load cannot be more than 80% of the circuit breaker. They're reciprocals of each other. So 15 amp times 120 volts is 1800 volt amps. And then if it's a 15 amp circuit breaker, a continuous load would be 80% of that. You take the 1800 volt amps times 0.8. But since it can only be loaded to 80% of its rated capacity, the maximum initial connected load should be not more than 1440 volt amps as shown by the calculation below. So here's their initial 15 amps times 120 volts, 1800 volt amps, times 80% is 1440 volt amps. Note you'll learn more about branch circuits and residential wiring, including calculating circuit loads in Module 26.111, residential wiring.